Hi everyone, welcome back from your reading week in whatever form that might have been. Before the reading week, we learned a whole bunch of information about linear kinematics. And now I hope you've had a chance to watch those videos and check your understanding, because this week we're basically applying the same concepts that we learned in the linear kinematics week, but now we're talking about angular motion instead of linear motion. So in this first lecture video, I want to talk about angles and the different units of measurement for angles. I also want to talk about angular motion in general, and then finish the video with angular position. Before we talk about anything angular, we need to know what an angle is. And quite basically, an angle is formed by the intersection of two lines, two planes, or a line and a plane. And the term angle refers to the orientation of these lines or these planes to each other. The Greek letter theta is used to represent the angle. Now, there are different units of measurements used for these angles. The most common is degrees, which you're probably familiar with, but there are also radians, which is a measure of the arc length of a circle divided by the radius of the circle. So that would be radians over here. You have your arc length divided by the radius. And then finally, there are revolutions. So let's take a little deeper dive into each of these units of measurement. So first we have radians. A radian is a measure of how many radii are in an arc length. And 1 radian is equivalent to 57.3 degrees. That is another magic number that you'll want to remember. And to calculate a radian, you divide the arc length by the length of the radius. And the important thing to know here is that radians don't actually have a unit. They're just radians. And that's because the units of arc length, in this case meters, and then the units of the radius, also meters, just cancel each other out. So there's no unit left for radians. And one last thing about radians, pi is a special number here that represents the ratio of a circle's circumference to a diameter. So if you think about it, pi times a radian is equal to 180 degrees. And you can try the math for yourself to confirm what I'm saying. Multiply pi by 1 radian, which I just told you is 57.3 degrees, and you should get 180 degrees. So our next unit is degrees. In a coordinate system, this is typically what the layout would look like in terms of degrees. You start at 0 degrees horizontally, and any rotation counterclockwise is positive, and any rotation clockwise is negative. And we'll learn why this is the case in a few slides. An arc of 180 degrees would just look like a straight line. And then a complete circle would be an arc of 360 degrees. The last unit of measurement for angular motion is revolutions. And quite simply, 1 revolution transcribes an arc that is equal to 1 circle. Revolutions are not as commonly used to describe angular motion because they're not really precise. But a couple examples would be a spin in figure skating. That's based on the number of complete turns, aka revolutions. Same with snowboard or skateboard tricks. So let's just look at the relationship between all the units that we just discussed. So 90 degrees is equal to 1/2 pi times a radian, which is equal to a quarter revolution. Okay, that's what this is showing you down here. 180 degrees is equal to pi times a radian, which is equal to a 1/2 revolution. 270 degrees is equal to 1.5 times or 3/2 times pi times 1 radian, which is equal to 3/4 of a revolution. And then finally, we have 360 degrees, which is a whole revolution, which is also 2 pi radians. Okay, so that's enough for units. Let's talk about angular motion now. Now that we know the definition of an angle and all of its units, let's relate that to angular motion. So you can think of angular motion as a motion about an axis of rotation. So I've talked about this before, but what is an axis of rotation? Well, it's this imaginary line that's always perpendicular to the plane in which the rotation occurs. So if you hold your arm out horizontally in front of you and you rotate it outwards, you're rotating your arm or your shoulder about this vertical imaginary line that sort of runs right through your shoulder. So in this case, the motion of your arm is a rotation in the transverse plane about a vertical axis. So I said I'd explain this idea of positive and negative directions of rotation, so I should probably do that now. Clockwise and counterclockwise are common terms that we use to describe the direction of a rotation. Now, the problem with this convention is that it depends on your viewing point. Imagine that we're sitting across the table from each other, and we're both looking at the needles turning on a clock. They would be turning clockwise for the person who's facing the clock, but then the needles would be turning counterclockwise for the person sitting at the other end of the table, because we're both looking at the clock from different directions. So for the same angular displacement, one person would describe it as being in a clockwise direction, and the other person would describe it as being in a counterclockwise direction. So obviously that doesn't really work. Thankfully, there are other ways to describe the direction. So remember from the previous slide that I said that an axis of rotation is always perpendicular to the plane in which the motion occurs. Well, here you can think of the axis as being like the axle on a bicycle wheel, whereas the plane of motion is the spokes of the wheel. So all these little spokes here would represent the plane. And along the axis of rotation, you need to establish a positive direction. So if you situate the thumb of your right hand so that it points in the position directly along the axis of rotation, then the direction in which your fingers just naturally curl is the positive direction of rotation. So you can even try it for yourself here. If you put your right hand up against the wheel on this slide, your thumb will point in this sort of direction towards you, right, with the axis of rotation. And your fingers will naturally curl in this counterclockwise direction. And that's the positive direction of rotation. So this is the technique here is called the right hand rule or the right hand thumb rule. So let's take our clock, for example. First, you should try to define what the plane and the axis of motion are. So the plane of motion is the face of the clock, and the axis of rotation is a line through the plane or through the clock face. So let's apply our right hand thumb rule here. That's me applying it. If the positive direction along this axis is established as pointing out of the clock face towards you, then the positive direction of rotation is counterclockwise as you're facing the clock. Right? So this line here is the axis of rotation of those needles turning around the clock face. And so your fingers are pointing in that positive counterclockwise direction. So thinking of this right-hand rule in terms of a coordinate system, you can establish a positive direction about each of the three axes. And you can try it by pointing your thumb in the same direction as the vertical y-axis, for example. So with your thumb pointing upwards, you can see that your fingers curl in the same direction as the arrow on the graph here, which is counterclockwise. And you can try that for each of the three axes. Just make sure that your thumb is pointing in the same direction as the arrow in each of the axes. Okay, so we've discussed units and direction of motion. Now let's talk about different ways of describing and calculating angular motion. Let's first talk about angular position. Angular position refers to the orientation of a line with another line or a plane. Now, if that other line or that other plane is fixed and immovable relative to the Earth, then the angular position is what's called an absolute angular position. For example, if you take your forearm, then the angle that your forearm makes with this sort of imaginary horizontal plane, that would describe the absolute angular position of your forearm, because that horizontal plane is a fixed reference. So another way of describing an absolute angular position is a segment angle. So it's just the angle of your forearm in this case. If that other line is actually capable of moving, then the angular position is a relative angular position. So for example, the angle of your forearm with your upper arm describes a relative angular position of your forearm or your elbow joint angle. So in this case, both the lines are capable of moving. So it's a relative angular position, or in other words, a joint angle. So here's a visual comparison of segment versus joint angles. On the left, you see that each angle is formed between one segment. For example, your upper arm and this imaginary horizontal line. So these are called segment angles because the angles are formed by one segment and an imaginary line that is fixed and immovable. Now on the right, you see that the angles are formed between two segments that are relative to each other. So for example, the upper arm and the forearm form an angle at the elbow. And this is a relative angle, right? Because both the lines are capable of moving. So segment equals absolute angles, joint equal relative angles. Okay, great. So here's an example of a joint angle and a segment angle. And I invite you to pause and think of the difference between the two angles that are shown here and figure out which one is the absolute angle and which one is the relative angle. So what do you think about the knee joint angle here? That would be your relative angle because it's formed between your thigh and your leg, two lines that are moving, right? And what about this trunk angle here? That's an absolute angle because this angle is formed between your torso and this imaginary horizontal line that's fixed. So that's an absolute angle. Awesome. One last example of absolute and relative angular position. So this shows you that for the same angular position, right, these two pictures are of the same lower limb position, you can describe the position of segments and joints differently. So notice that the positive direction is established in both the absolute and the relative diagrams, if you want to call them that, as being counterclockwise. So a counterclockwise movement is positive in this case. So if we start at the hip, you can describe the absolute position of the thigh in reference to a line at the hip as being negative 70 degrees, and negative because of the direction of the arrows. And for that same position, you could describe the position of the thigh in reference to the trunk. And that would be a relative position of 160 degrees. Now, if we look at the knee, the absolute angular position of the shank segment is negative 100 degrees. So that's this angle down here. And the relative position of the shank in reference to the thigh in this case is negative 135 degrees. So with those numbers in mind, I invite you to try to describe the absolute and relative positions of the foot and the ankle on your own to confirm your understanding. Okay, so in this first lecture video on angular kinematics, we really focus on understanding what angular motion is, reminding ourselves of what an angle is first, and the different units of measurement for angles. And then we talked about angular position. So in the next video, we're going to keep going with those different kinematic variables, talking about distance, displacement, velocity, acceleration, all that good stuff. So stay tuned.